In this video I'm going to be talking about zero force members. Zero force members, or also called redundant members. Now, we've talked a little bit previously, or at least with this class, we've talked a little bit about why we have redundant members. And the idea is that the main reason we have redundant members is they're not redundant in every case. They're only redundant in some load cases. That's the main reason we have redundant members. Another explanation is that redundant members can be important for bracing, so that we don't have long lengths. We can have something to reduce the effective length of members, and that can be useful for bending. The longer the distance between supports, that increases bending stresses, and compression is also affected by the longer the length, the more likely it is to buckle. So that's where we can have bracing. But the main reason, if we had to explain why the redundant members exist, we'd say these members are there for different load cases to what we see here. So in this particular case, that we'll have redundant members or zero force members, but that's not always going to be the case. Now there are two main ways that we can see that something is a zero force member. So I've got two past HSC questions that both feature zero force members, but there are two main ways that we can see. So the first main way is if we ever have something where if we have a truss, actually I'll draw this truss here. Okay, so if I apply a load, an external load, if I apply an external load here and just to make it a little bit longer, I'll make it external load here, and let's say my reactions are going to be here and here. These are my reactions, right? So I've got my loads and my reactions, right? Now in that case, there are two major ways that we get redundant members. So this member here is going to be a zero force member. That member there is going to be a zero force member. And both of these, remember my reactions, just to make this a bit easier. There we go. I just want to make it really clear. Okay, so these members here are going to be redundant. Okay. Hopefully nobody had started to draw too much of that drawing. So I'm just going to move my reactions. I just want to make it somewhere that's really clear and really obvious. So the two main ways that we can have, I'll have another video which I'll include to this, I'll link to someone else's YouTube video. It's just a recorded speech video, but I've been using it for years and I think it has some value. So the first one is, what we're going to say is we have, I'll start with this one as our first one, is anytime we have forces meeting at a corner with no external forces, right? If we have forces meeting at a corner with no external forces, like we have here, well, just for the sake of it, we're going to call this member A and this member B. If member A has some amount of vertical component, doesn't matter if it's up or down, just for the sake of argument, we're going to say member A has some amount of vertical component. Well, if that's the case, then member B can't resolve it. Because if we look at some of the forces, if we take the method of joints, this is where method of joints can be useful. If we take the method of joints around this location, we can see that we have forces that can't be balanced. If we have any amount of vertical component here, B can't have vertical component. So if B can't have any vertical component, it means A has to be zero. The same is true in the horizontal direction. If B has any value whatsoever, if it has 1 Newton, well, B has to provide a horizontal reaction, or it has to provide something to balance that force, and it can't because it's vertical. So this is also will end up being true even if it's at an angle. If there's only two members at a point, they can't have any value. So if there's only two members at a point, they can't have any value. Now, once we have, if we introduce an external reaction onto this, now there will be a reaction. So if I now have this force of, let's say, 100 newtons, well, now I say that A has to be 100 to balance that. A equals 100 in order to balance that. But B will still be a redundant member. It will still be zero force, because there's no horizontal force for it to react to. If this was diagonal, in that case, it doesn't need to be redundant at all. Both of those members could be non-redundant. But that's what we're looking at here, is that when we apply a force to a corner, suddenly it's not redundant anymore. That's our first situation. So if we have a corner, if we have two members meeting with no additional forces, so I'll write that down as a rule. I'm sure Copeland has a good explanation somewhere. If I knew that, if I was smart, I would look that up first. If I say two members okay. The next situation is this one here, right, where I have three members that are supplementary, right? So see how here we have this makes up 180 degrees, right? We have, in this case, it's pretty easy. I can use green for this one. We've got 90 degrees plus 90 degrees. It's going to be equal 180 degrees. It's the same situation that if this, we'll call this C for the sake of argument. If this member C has any amount of force whatsoever, there's nothing to hold that point, that joint in equilibrium. If we look at that joint, if we draw it out here, so let's assume that C is going down, right? We have these two members here. We'll call them, I'll label them D and F. D and E, sorry. If I have D and E, and this is C, what we can see is that D has no vertical component, E has no vertical component. So because they have no vertical component, means if C has any amount of vertical component, even 1 Newton, it's going to push this joint down and break it. Now again, if we add a force to this, if we add an external force to this, then it will be fine, right? In this case again, if we add, let's say we're going to draw this as 100 newtons, well now C will have to pull up 100 newtons to maintain that equilibrium. So the point is, it's only when there's no external force that this thing is in equilibrium. Now initially, when I first drew this, I drew this with a member here, right? I drew it with an external force here. Now, even in that case with the external force here, we still have the situation that if A has any vertical force at all, it will still cause it it will cause this joint to break, to pull apart. It can't be in equilibrium. So this is sort of drawing a little bit on method of joints, and I don't really like to talk about method of joints, but this is to try and help you to understand how to recognize when things are zero force members. So if we have a corner where two members meet and no external forces, even though this side has a force applied to it, this side here can't be the answer. What's going to happen is that the vertical here is going to be matched by, the external there is going to be matched by a force here and here. So it's going to have to be this member that provides the reaction. Yeah, it provides the internal force in order to maintain the equilibrium. I think I maybe misspoke, but you get the idea. So that's going to have to be what balances. A can't do it, because if A has any amount of force, B can't resolve it, B can't keep it in equilibrium. If B can't resist it and keep it in equilibrium, the thing's going to explode. Same thing here, right? If C has any amount of force, D and E, they just don't have any vertical components, so they can't keep it in equilibrium. Okay, so what are we looking for? When we're talking about so if we have a shape that looks like this, or a shape that looks like this. So I'll draw that again. If we have a shape that looks like this, or a shape that looks like this, we're going to have zero force members. Or redundant members. Now, it doesn't matter if the thing is on an angle. Again, if I have something like this, I'll even stretch that out a little bit more. actually looks worse. So if this is 45 degrees and this is 135 degrees, it's still gonna count. So what we have here is if we have I'm just going to call this supplementary angles, right? So if we have a supplementary angle, it has to equal, so members meeting at a supplementary angle. Members you know what, I'm just going to write 180 degrees because I'm not confident in my spelling. 180 degrees with no external forces. Now, so 3 members meeting with no external forces. But what is interesting is we can actually have a zipper effect. So let's have a look at our HSE questions, and we're going to look at here. Can someone tell me where is the zero force member in this question? The 2014 paper, where is the zero force member? Okay, so I can see what you're saying, because CF meets, because it's meeting, so okay, up the top, if we're looking at CF in the top half, that's on a supplementary angle, it doesn't equal 180 degrees. And down the bottom, it's more than 3 forces, more than 3 members meeting. So for the moment, it might be, but for the moment, we're not going to assume it is. The one that stands out to me is DF. Yeah, can you see that now? The DF is going to be a zero force member. You know, I'm going to do it like that because I don't want it to show up on the camera. Okay, so that's going to be a zero force member. Now, we can have a look again, and we can still say, well, okay, so CF here, it's still not a supplementary. Yeah, so it's not a straight line angle. And here we have 1, 2, 3, 4 forces meeting in that location. So it's reasonable to assume that that's going to have some amount of force there. Yeah, I think that the other ones should have forces. I haven't calculated everything else, so could be, but I'm going to move on. On the 2015 question, where is the zero force member we can see?
It's FD again.
It's FD again, yeah. Because this here is a supplementary angle, okay? And then what happens now? So when FD disappears, if we just imagine that FD isn't there, for the moment I'm actually going to just remove this from the whole drawing. Do we have another zero force member? Okay, so why is DEF, why is DE and EF, why are they not zero force members?
There's an external force. Yep.
There's an external force, exactly right. So if I removed this 750, then yes, we could assume that those outside forces are in fact, they would be zero force members, right? But we have another, this one here is also a straight line angle. Yeah, 3 forces meeting together at straight line angle. I'll draw it in. Yeah, do we see it now? We have three forces meeting at the supplementary, they add up to 180 degrees. Okay, so then we can see that often in this sort of shape, right, in this sort of shape, if you start removing one member, you can find that a whole bunch will act like a zipper, and we'll just have a whole bunch that just start disappearing. Now I'll include some other examples in Google Classroom. I'll put up a YouTube video that goes through multiple examples so you can see them. But I just wanted to look at these two, and we've now got 2 rules. So we can say if we have 2 members meeting at a corner with no external force, if we have 3 members meeting at 180 degrees with no external force. That's our rules, the 2 rules that we're looking for. What I want to do is, How do you write that in the HSC? Well, you can just write 0 by observation. That's one thing you're allowed to do. But what we're going to do is we're just going to try and solve this as if we're going to solve these two just as though we were doing it in a normal truss. We're just going to try and solve it, and without just saying by observation, we're going to actually demonstrate that they're 0. So I'm going to get rid of this one here that was my example, and we're going to start with a new one. Okay, so I want to find DF. How am I going to find DF? So what's my first step? First step with trusses, we're using method of sections. We need a...
Cut it, like,
Exactly right. We need a section line to cut through. It has to be something that cuts through DF and can't cut through more than 2 other members. So we could go this way. That's cutting through 4 different members though. That's too hard, right? And we can cut that way, yeah, but generally we're going to... I'm not saying it should always be vertical cuts, but often it will be a vertical cut or a vertical-ish. Anyway, so what we're going to do is we're going to put our cut here. Now, which side do we want to take? Do we want to take the left or the right? We want to take the right-hand side? Right-hand side is a great idea. The big problem with the right-hand side is that this is unknown, currently unknown. We'd have to calculate that reaction in order to solve it. Nothing wrong with that, right? There's nothing wrong with calculating that reaction. But I'm going to say if I have to choose between calculating a reaction or using 2 external forces, I'll take the two external forces, please. I'll also say it would just work better for our calculation because I had a brief discussion yesterday with a student and I think that it's going to work a lot better if we just take it from the left-hand side. But good ideas that we're thinking about. Okay. So first thing we've done is we've cut. Now we're going to draw. You don't have to draw, but I like to draw what our thing looks like. Now we have some internal members, but I don't really care about internal members, right? Internal members don't count, so we can just ignore those internal members. Don't count as far as I'm concerned. What we have instead is we've got 225 newtons, so it's probably kilonewtons, one would presume. Yep, kilonewtons. And we've got 30 kilonewtons going down. And we've got, now we're going to make assumptions. We're going to assume CD is in tension. And we're going to assume FD is in tension. And we're going to assume FE is in tension. Okay. Now, what is our target? What are we trying to find? What are we here to find? Well, we're here to prove something. We're here to prove FD, right? So FD is going to be our target. So FD is our target. CD and FE are our distractors. Is there a spot where CD and FE meet?
E.
Exactly right. Okay, so that means we're going to take our moments about E. Now, our distances, we need to know our distances. We've got this distance here. So what I'm going to do is I'm going to extend that line forever up and down, and I'm going to find where is it perpendicular to E. Yeah. So what is that distance? 3/4 of 75. 3/4 of 15, right? Could anyone with the calculator type that in for me? It's like 10.5, I think.
11.25.
Terrible. I'm disappointed in myself over that one. As disappointed as I am in this pen. And that is a lot. They're all blue. All of them are blue. We're running with it. 11.25. 11.25. I could have even done it in green, because we're doing distances. Anyway, I think in this case the green is more visible to the camera than the black is. 11.25 meters, yep. And then this distance is obviously the same as above, 15. What about our distance to FD? What's our distance to FD? This is where drawing the angle accurately probably matters. Now, what another person might do is they might calculate the distance. Oh, that's in red because we're assuming tension. Okay, so what we're trying to do here is we're going to find out what is this distance here. So I'm extending that force out to forever. Yeah, I'm extending FD out forever in either direction. And then I'm finding what is the perpendicular distance, which is this here. And then I can measure it. Okay, so what does that distance look like? I'm going to draw a little diagram here. So I have 60, 60, extending it like that. Okay, hopefully that's clear. So what is the base of my triangle? We're being told in the drawing, I think, that we can measure these off at 30 degrees and 30 degrees. What is this length, the length of this triangle?
7.5.
7.5, excellent. And we'll call this distance here, we'll call it D. Right, what is that distance? If I had a 30-60 triangle, right, like this, I would say 30, 60. I know that if this is 100%, the long side is 100%, the short side is how much? It's sine. Does that make sense? Observer Jason's tan. Anyway, 50%. So what's D going to be?
3.75.
Exactly right. D is going to be 3.75. So D equals 3.75 equals 3.75 meters, right? And I'm just going to draw that in here like this. Why am I writing that in red rather than green? Because it's calculation. Anyway, okay, so we've got our distances. Now that we've got our distances, we can now actually do our calculations, right? So I'm going to do that. Hopefully the camera can pick it. Right here. Okay, so sum of the forces clockwise equals 0. Where are we taking sum of the moments clockwise equals 0? Where are we taking moments about?
E.
E, thank you. So the sum of the moments measured from point E equals 0. 0 equals, so we've got how many external forces? 2. And we have these 3 cut members. Now, we don't have to show the cut members, but I'm going to show them because I think it's important to remember what we're doing here. So what we've got is, that X is confusing. Okay, so we've got CD multiplied by 0 plus, or generally we're at minus, but it doesn't matter, FE multiplied by 0. Then we've got FD. Now, what did we assume for FD? Did we assume that it's positive? Is it clockwise or anti-clockwise? Let's put our finger on E and spin it. Positive or negative? Positive, clockwise. Okay, and its distance is, we measured D. And I could put that number in, but I want us to see where we're getting that value. And then we've got 2 external forces. We've got 22.5. How far away is it?
From
E.
15.
Excellent. And is it clockwise or anti-clockwise?
Clockwise.
Okay.
Positive.
And then we have 30, which is 11.25. Okay, is it clockwise or anti-clockwise?
Well, it's negative.
Anti-clockwise. Okay. So if we type all that in, if you can give me the answer, that would be fantastic. I am going to write that as, so this is 0, 0. We're going to get 3.75 FD. That's positive. Plus 3375 minus 30 times 1.25. There we go. Okay, so we can move FD over to this side. Right, I'll call it minus 3.75 FD equals, what's 3375 minus 3375?
0.
Wow.
So we're able to prove that it's a zero force member. Now, I don't expect people to do that. I don't expect people to do that. I expect people just to write zero force member by observation. Yeah? Zero by observation is fine. Now, I don't know if I'm going to bother with the other one. Is it worthwhile for me to do the other one? Do you want to prove that as well? Or if I don't see any particular interest, I'll just leave it. Yes, okay, we're going to do one more.
Did you write 0.25 on the last one?
Oh,
Yeah.
because there is slight difference. Yeah, okay, let me type in
No,
the...
it's 0.5, I'm pretty sure.
Yeah, sorry.
But if someone looks at the work,
Thank you. Excellent catch. Appreciate that. That's as bad as my trigonometry earlier. To excuse my trigonometry while I'm cleaning the board off, my excuse is I just don't use trigonometry. I just look at it and I know it's a 30-60 triangle. I just do it by known values. So okay, I'm actually going to remove this whole question now. And we're just going to use this whole side of the board. We don't even need this heading anymore, and we're going to do this one. Okay. So, we're going to find FD again. So step one is we are going to choose a cut. I'm going to choose the cut for us. We're going to cut here. And I'm going to redraw it. That's what our cut looks like, something along those lines. Now, I'll label everything. So we've got assuming tension, so assuming things are pulling out, FD. We've got CD. We've got FE, or EF. Okay, and we've got an external force of 750. Now, the problem is if we take this left-hand side, I mentioned this earlier, if we take the left-hand side, so our target is FD, and we have CD and EF, yeah? So we want to eliminate CD and EF. Where do they meet? At E. Yeah? So when we do that, what ends up happening is we can't get an answer because everything just multiplies by 0, right? Everything is going to multiply by 0. So if we do some of the moments about E equals 0, we're going to have 0 equals CD 0 plus EF 0, 750 0, and then we're going to have some number. We'd have to figure out what this distance is. Whatever this distance D is. We might still have to do that in a second. And we'll have FDD. Right? Do you see how it's going to be 0, 0, 0, FD equals 0? Yeah. So, just to make it more interesting, we can take it from the other side, but if we take it from the other side, we have to find the reactions, and that's a bit of a pain. So what we'll take a look instead is we'll try and do CF and prove if that one's 0. Hopefully there's enough forces for CF.
so that mean you have to change the cut as well? Or?
Yep, we do, because we don't cut through CF. It's going to be the same, it's going to be just as bad. So we're going to cut this way this time. Okay, we will have to find reactions. I'm not really interested. You guys don't make you find these reactions already? No?
Yeah.
You did? If you can tell me the reactions, that will save me some time. And I can talk about things that are more interesting.
That's kind of full sheet, isn't it?
Hold on, I think it's-
I think we did the full sheet, didn't we?
I just wrote that last one. Trying to do that.
So I think we did reactions the full sheet.
Yeah, so do you have it in your book?
Probably
I
not.
printed it on a piece of paper, but I don't think it will.
If I want to work it out, I have to actually know which one's the pin and which one's the roller.
So is the top one meant to be BD, or am I wrong?
Is it the 2015? Yeah. Right.
Top one is... The top one is this section here. I see how it looks like BD,
Yeah.
but the C is in the way.
Yeah. Okay.
So it's the same line.
Yeah.
Okay.
Do you just want the final value?
I do.
It's 3,450 newtons.
Which one's that? A?
Yeah.
3,400.
50.
3,450 newtons. And then B will be like this way. Okay, so I can, what I'm going to do instead is for this one, we're going to actually break it into components anyway. So we'll say this is 12, if we've got 12 down and 1,200 and 750 down, means I'm going to have 1950 up to keep that in balance. And then I'm going to have another component. If the only horizontal force I have is 3,450, this is also going to have to be 3,450, but the other way. Yep. Okay, so we now have our forces that we need to solve this. So, okay, so what we're trying to do here is we're trying to find CF. That's our goal. So if we're trying to find CF, what are our two unknowns? CD and AF? So where do they meet?
A.
At E. Okay. At E. Okay. So, measuring our distances, we're going to take the sum of the moments about E. So say clockwise, sum of the moments measured about E equals 0. 0 equals. Okay, so we have measuring from E 1, 2, 3, 4, 5, 6, 7 different forces, right? We're going to eliminate some of them straight away. We're going to eliminate AF. And we're going to eliminate CD. We're going to eliminate this 3450 because it runs through E as well. My drawing's not fantastic, but it runs through E. So then we have four other forces. 1, 2, 3, 4. 4 forces that actually do anything. Okay, so we're going to have CF. To do CF, we have to know the distance from CF to E. We need to know this distance. So this is going at 45 degrees. We're going to call this T. Okay, so what I'm going to do to figure that out is I'm going to draw a triangle. So what I'm going to do is I'm going to say, well, if this is a 45-degree triangle, and this is 1.5 plus 1.5, and this is 45 degrees, again, I'm not even going to use trigonometry, I'm just going to say, well, if this is 3, this is going to equal 3 times 0.707, which is sine 45. That's the distance of D. Just to close that triangle off. Okay. So, what I have CF, and the distance is 3 times 0.707 equals 2.121. 2.121. So, I've got CF. Is it going clockwise or anti-clockwise? Put my finger on E and I spin.
Anti, so it's negative.
Negative. So it's minus. I have 1200. 1200 is how far away from E?
3.
Okay. Is it going clockwise or anti-clockwise?
Anti.
Okay, so it stays as negative. I have 1950. How far away is it? 4.5.
And that's positive.
And that's positive. Excellent. I will just, for the sake of the viewers at home, I will prove that it is in fact positive. And that was the worst plus sign I've drawn in a long time. Okay, the last force we have is this one here. 3450. What's its distance from E? So we can extend this line all the way out. If we extend that line all the way out, what's its distance? At the point where it's closest to E, what's its distance?
1.5.
1.5 meters. Okay, is it going clockwise or anti-clockwise? So putting my finger on E,
Anti.
anti, so it's also negative. Okay, so let's ignore. I'm going to bring this minus, put it over the other side of the equation. So I'm going to say 2.121 CF equals, I've got minus 1200 plus, so I've got minus 3600 plus 1950 times 4.5 plus 8755 minus 3450 times 1.5 equals 5175. Okay, if I take this number of 8775 minus 5175 minus 360, therefore CF equals a zero force member. Now, again, you're not expected to do this working out. You can just look at it and say by observation. It's an interesting debate among HSC markers to say, should we be giving marks for kids who just write tension? When we ask for the nature of the thing, we say, is it in tension or compression? And sometimes you can tell, you just get a real sense that there's no working out, that the kid has just written down tension and tension. And if he were, one of the two would probably be right. Yeah? Sort of like a coin flip. And we argue, well, should we be giving marks for that? Now, I would say that what you should do to get that mark, to explain to the marker, is you said, I have looked at this by observation. I haven't done any working out, but I've looked at this and I've said, well, given the forces that are here, I think it has to be this. So often we can look at a force and we can say, well, if there's only two forces in a location, if I have the corner of a truss like this, yeah? And I have a reaction that's going up. Let's call this one EM. Alina, is this going to be going down or up? EM, remember EM is going to be going up or down?
Up.
Okay, so we've got a reaction pushing up. This SC doesn't do vertical, so EM is going to have to be able to maintain the equilibrium at this location.
Down.
So it's going to have to be going into the node, yeah? If it's going into the node, is it in tension or compression? Compression. So you could say EM is in compression by observation. Just that simple. Yeah? So that's how you could demonstrate in those sorts of scenarios. You can say EM is in compression by observation. And that's a mark. That could be 1 mark out of 6. Every mark counts. Okay, so that's it for Zero Force members today. The key takeaways are that if there are 2 members that meet in the corner with no external forces, Zero Force member. If there are 3 members meeting at 180 degrees with no external forces, that's a Zero Force member. That should be good enough.